This should be our last video for this section. We have example 10. We're still determining if the intermediate value theorem applies. We haven't actually used it yet. We still need to learn when we are able to use it. So if it applies, it should be continuous on a closed interval. So let's find out if there are any places where this function is discontinuous. Alright, just looking at these functions, linear, that's continuous, continuous, continuous. Alright, we already have a point. It's discontinuous at x equals 5 because there's a vertical asymptote there. Now the only other sections that we'll have to check are -2, 1, and 4. So let's go ahead and check each of those. So the limit as x approaches -2 from the left, okay, that's going to give us -2 times -2, +4, equals 5, which also equals the function value there. Okay, and what's the limit as x approaches to -2 from the right? 2 squared, 4 plus 1 is 5. So it is continuous at x equals -2. Alright, now we have the limit as x approaches 1 from the left. That'll be 1 plus 1 is 2. Okay, the limit as x approaches 1 from the right, that should be a plus sign, okay, equals 3 times the square root of 1 is 3, so it's not continuous, and this is also equal to f of 1. It's not continuous there, so I'll write that over here. X equals 1. The left-hand limit does not equal the right-hand limit. And now we have the last one, limit as x approaches 4 from the left. 3 times the square root of 4, that's 6. And then we have the limit as x approaches 4 from the right, which is 6 over 5 minus 1, which is 4, or 5 minus 4, that's 1, 6 over 1, 6, which is equal to the function value there, which means it is continuous. Now we should have enough information to answer all of these. So does the IVT apply on this closed interval? Yes, because it's f of x is continuous on that closed interval. And be specific. Okay, practicing writing these things will help you remember when you use it. Alright, -3 to 0, same thing. There's no discontinuities there, so f of x is continuous on that closed interval. So the IVT applies. -1 to 1. Alright, so we know that f of x is discontinuous at x equals 1, but it still could be continuous. So does the limit as x approaches 1 from the left-hand side, does that equal the function value? So that's no, okay? We could say that the limit as x approaches 1 from the left does not equal the function value at 1. Okay, that's a reason why it's not continuous at that endpoint. Now looking on the other side though, this would be yes. Yes, because on the other hand, the limit as x approaches 1 from the right equals the function value. So it's continuous at that endpoint coming from the right-hand side. So the IVT would apply on this case. Now for the last one, this is no, since f of x is discontinuous at x equals 5. There's a vertical asymptote there. Alright, so now that we've figured out when we can use the IVT, let's actually use it now. Prove that it must have that without actually finding the root. Okay, now let's say f of x is continuous for all values of x. Alright, now we need to pick different values. Let's say f of -1. What is that? 1, so we get -3. F of 3, 9 minus 4 is 5. Now, since f of x is continuous on the closed interval from -1, so let me just clear that up. specifically what we need. F is continuous on -1 to 3, that closed interval. F of -1 equals -3. F of 3 equals 5. So that means by the IVT, f of x must hit every value between -3 and 5. Okay, we need to write that by the IVT. Since f of x is continuous, we have these function values by the IVT. There must exist, I'll write out the words, there exists some x equals c value such that f of c is between there, okay? So for somewhere, it has to hit every single y value in between -3 and 5. And because it must have a root, there has to be somewhere where f of c equals 0. Right? There has to be at least one x equals c that equals 0, because 0 is between -3 and 5. All right, let me try explaining that again. Show that there's a positive real solution. All right, we only know how to work with one function right now. So I'm going to make that one function by subtracting these two. F of x is continuous for all real numbers. We're trying to show that there's a positive real solution. Okay, so that means that for somewhere, this should equal 0. All right, if I try let's try f of 1, maybe that'll work. F of 1, plug that in, I get 1 minus 1, 0, minus 2. Let's try maybe f of 2. 2 to the 5th, I think that's 32. Minus 2 is 30, minus 2 is 28. All right, so that's enough information. Since f of x, I'm going to write this out in all the words here. I'm going to use some symbols. Since f of x is continuous on a closed interval from 1 to 2, this means there exists. So instead of writing that out, I'm just going to write that E. Okay, there exists some x equals c, some specific x value on that interval, such that the y value is somewhere between -2 and 28, which could include 0, okay, by the IVT. There we go. All right, let's keep going. Let's see if we could do another one. Prove that there's a solution, f of x equals 4, for some element in between 0 and 4. All right, let's mention our beginnings. We know x squared and cosine are continuous for all real numbers. F of 0 would be 0 plus cosine of 0 equals 1. F of 2 would be 4 plus cosine of 2 pi, okay, which is 1, so that's 5. All right, since f of x is continuous on 0 to a closed interval, there exists an x equals c, some constant value on that interval, such that f of c is somewhere between 1 and 5, which includes our 4, which we were looking for, by the IVT. All right, great. We have one more example to cover. All right, this is a modified part. It's not the whole free response. We'll get more into this further in the year. But this is actually from the 2007 AP exam, which I took and passed with a 5. Oh yeah. All right. So part of this, example 14, we have this table of values, and you'll see on the free response, they like to put graphs, they like to put the verbal descriptions, numeric, which would be a table, and they have equations. So this one has a table or a tabular representation. All right. The functions f and g are continuous. Great, that's helpful. The table gives the values and their first derivatives. What is that? Oh, well, it doesn't matter for now. The function h is given by this. Probably important. Explain why there must be a value r between 1 and 3 such that h of r is -5. Now, notice it doesn't tell you to use the IVT. You have to know that. All right? So we know that h of x is continuous. Since f and g are continuous for all real numbers, h of x is continuous for all real numbers. You could write out for all real numbers, but I like to use the symbols because it shows how smart I am. Now, we know it has to be on this interval. Let's test the endpoints. H of 1 equals f of g of 1 minus 6. Okay, that would be f of 2. F of 2 is 9 minus 6 equals 3. All right. Let's try h of 3 now. Now this is showing, 1, that you know how to use the IVT. 2, it's showing you know how to use composition of functions. And 3, you can use a table to find the values. Okay, so this involves a lot of skills that you have to have. All right, look at that. -5 happens to be in between -7 and 3. So by the IVT, there exists some x equals r value on 1 to 3, that closed interval, such that h of r equals -5, since we could say -5 is in between -7 and 3. There you go. So we're at the end of this section. We're actually at the end of our chapter. We're finally going to start moving away from limits and on to something much more exciting. Have a great day.